Hi everyone, I'm Nikitas Maragos, a PhD candidate at the Department of Informatics at the Aristotle University of Thessaloniki in Greece. What I'd like to present today for the 2022 14th IBMSP workshop is our paper called Electric Load Demand Forecasting on Greek Energy Market using Lightweight Neural Networks. The research for this paper was conducted in cooperation with Maria Tselepi, Nikolaos Passalis, Apostolos Adamakos, and Professor Anastasios Stefas in the context of Malena project. The primary purpose of this research is the creation of a lightweight system that can accurately predict next day's load demand of Greece on an hourly basis. The presentation is structured as follows. First, we make a brief introduction to the electric load demand forecasting problem. Moving on, we describe our proposed method, we present our experimental evaluations, and finally, we draw our conclusions. So, electric load demand forecasting is the task of forecasting the aggregate expected electricity demand. It is a vital task accompanied by many applications, and so it is of crucial importance to develop methods for more accurate ELDF. Deep learning lately is the state of the art for a plethora of domains, and that is the case for ELDF tasks as well. In fact, there are several works for Greek energy market as well. In the vast majority of these methods, two assumptions are made. It is considered that any data before the target day are available and can be utilized, and that real weather information of target day is considered available as well. In this work, we deal with ELDF problem on Greek energy market on an hourly basis, considering a real case scenario in which we use real data provided by the Greek Public Power Corporation without the unconditional availability of prior knowledge before the target day, and we retain the assumption of non-weather information on target day since its solution relies on another task known as air temperature forecast. To be more precise, at the top of this image, we clearly see the common scenario, while at the bottom, we present a more realistic approach where some data are completely unavailable and some others are occasionally available. So, our objective is to provide effective models in a real case scenario. According to Greek PPC, a model is a successful one if 99% of its predictions have a mean absolute percentage error below 10%. So, we propose a lightweight neural network with a novel loss function. First, we utilize the successful model called ResNet Plus, and we adapt it to our scenario so as to use it as a baseline model. Despite its effectiveness, it is a highly complex and hence computationally and memory demanding, as well as time-consuming model. Both training and inference time are of utmost importance since the final model will be used in production. So, we propose a lightweight multi-layer perceptron model trained with a novel loss function. This MLP model consists of two hidden layers with 300 and 100 neurons respectively, while the output layer consists of 24 neurons. Now, when it comes to the input of our model, we have focused basically on 3 past days. These days are 1 day, 1 week, and 1 month prior to the target day. For these 3 days, We use both their load demands and their temperatures. Also, we have used some information about the target date and about the target date itself, such as the real temperature data, whether it is a weekend or not, whether it's a holiday or not, and what day of the week it is. In the Greek energy market, each Thursday, previous week's data are being published. This delayed availability creates a gap of 4 to 10 missing days, and so our first priority will be to fill. So we need 10 model plus 1 extra for the target day. In total, 11 models. An example will help us to understand better how we work. Suppose that today is Wednesday, 11th of March. So the most recent load data are those of 1st of March. We first use the MLP model 0 to create a prediction for the 2nd of March. Then, for making a prediction for the 3rd of March, we will use the MLP model 1, but the input feature L day will basically be the prediction of the 2nd of March. This procedure will go on until we reach our original target day and by making the appropriate adjustment for each case. Now, as mentioned earlier, Greek energy market has a restriction for the May predictions, and that is the reason why we created a novel loss function that can handle this. By using this new loss function, we combine May with an extra added that provides a higher penalty for May bigger than C. Now, let's continue with the evaluation metrics. 3 groups of MAPE errors have been created. Errors below 10%, errors between 10 and 15, and errors above 15. A successful model would achieve at least 99% of its errors to be in the first group. Furthermore, we use MAPE and some other metrics such as training and inference time, complexity in terms of floating point operation per second, model parameters, and required memory for both baseline and proposed method. For the evaluation, we evaluate the performance of both models in the common scenario used in the literature, but in the real case scenario of Greek energy market as well. We use 5 years of data for training, 1 year for validation, and 1 for testing. With the help of validation set and with the grid sets, the parameters of our novel loss settled to be A equal to 1, B equal to 0.4, and C equal to 2. Now let's observe the results. In both typical and real scenarios, our proposed model achieves a better MAPE. Considering MAPE groups, ResNet Plus is successful with 99.47% on average, and so is our lightweight model with a slightly better percentage. Moving to real case scenario, ResNet Plus is still successful with an average MAPE of 99.24, and so our lightweight model with 99.12% on average. Now, by checking the remaining metrics, our proposed model is significantly more efficient compared to the baseline model, and especially considering the inference time, where it's almost 7 times faster. So, to sum up, we dealt with ELTF on Greek energy market and proposed a lightweight model with a novel loss function. To the best of our knowledge, there is no other work that uses data of Greek energy market in a realistic setup. Last, our proposed model achieves better performance considering the NAEP metric and is significantly more efficient and faster. We should not fail to mention that this work is co-financed by the European Regional Development Fund of the European Union and Greek national funds through the operational program Competitiveness, Entrepreneurship and Innovation under the code Research, Create, Innovate. Thank you for your attention.